Hi friends, mixture of experts is the trick behind today's largest language models. You must have heard of many recent improvements in MOE, such as G#, switch transformers. Early this year, DeepSeek also has its own implementation of efficient MOE. Scaling MOE is not only trendy, but also essential. MOE allows significant improvements in inference time, but the actual training also needs to scale up. Today, let's talk about the 2017 Google paper and learn how Google scales up the MOE training. Here's our agenda today. We'll first talk about what is MOE and the MOE setup in this paper. And then we'll talk about some fundamentals to prepare further explaining the problems. So for the fundamentals, we'll talk about distributed training and the conditional computation. With those fundamentals, we then will further explain the three problems that this paper is targeting to solve and its proposed solutions. And lastly, we'll talk about experiment results. Let's get started. So first thing first, what is MOE? MOE stands for Mixture of Experts. The intuition is that one task can be split into multiple subtasks. And for each subtask, the model has a subnetwork trained independently for that task. The way MOE does this is that it split it into two steps. First of all, it has a gating network that does the routing work. And then it has separate expert network, like subnetworks, trained for each subtask here. So the two-step works like this. First of all, the input data goes through the gating network, and the gating network worked as a router. It routes the input data to the right expert, and eventually the output will be either a weighted sum of the selected experts by the gating network, or the top one, the one expert that the gating work thinks works the best. So what's the difference of mixture experts with a traditional model? Traditional model can be think of as only one expert doing the job. There's no router, there's no gating network work as a router, there's only one expert. So as you can see, the benefits of using mixture of experts is that at training time, you are training multiple networks, experts. At inference time, you only need to activate a small number of experts. So it's you train that many parameters, but when at inference time, the computation actually is not that much. So here is how this paper set up MOE. Remember, this paper is from 2017, so at that time, attention wasn't as widely adopted as today. So they use MOE in RNN and LSTM. As you can see here, they are training multiple experts, and they are using a gating network as we just discussed. So what have they done differently? They did make some changes in the top K gating network. So instead of using a vanilla softmax gating, they added a noise component here. So basically, they have a weight specifically for the noise in the hopes that adding some noise will reduce the situation where one expert got reinforced and causing load imbalance. Next, let's talk about data parallel in distributed training. So essentially, data parallel means that when you have a large amount of data as your training data, so large that it cannot be stored in one machine. In that case, you actually need to partition your data into multiple shards so that each machine holds its own data. A typical data parallel has below steps. So first, you initialize the model parameters and then forward, backward. So this is the same as a single machine, right? And then you realize that different machines are training on different data and they will have different loss, different output, and then results in different gradient. So how do you make sure that you are only training one version of the model? That's when you do this all reduce work. It's quite important so that you gather the gradients from all the workers and make sure they're in sync. With this, you average all the gradients, make sure that each machines are going to be updated using the same gradients. Next is further computation with optimizer update, and then after that you do some zero gradients. So another concept here is the compute communication ratio. So remember previously we talked about the data parallel. There are 6 steps: model initialization, forward, backward, or reduce, optimizer update, and zero gradients. As you can see here, all the steps happens in local for the worker, except the all reduce part, where the worker need to communicate with other workers that host different data and then gather gradients from those other workers. So this is the only communication step of the whole distributed training for data parallel. And there's this concept of how much time and how much bandwidth you could spend on communication step versus computation steps. A GPU card measures this by bandwidth of communication and the flops of computation. Essentially, you have specs of hard limit of your GPU card for compute versus communication. So at training time, what you want to do is that you have a compute communication ratio that exceeds the card specs. What you don't want to do is that the communication step takes too long and your GPU idle. And then let's talk about model parallel. The difference mostly lies in that in model parallel, it distributes model parameters into different workers so that each machine hosts a different part of the model. Here's a comparison diagram. So the difference is that data parallel shards data and model parallel partitions the model parameters into different machines. And the communication part is that for data parallel, you only need to do the all reduce after forward and backward pass. But for model parallel, that requires more communication. Actually, in today's large language model, the model is usually very large, has billions of parameters. So model parallel is actually already widely used and essential for large language model training. Next, let's talk about the conditional computation. So for the traditional network, all the neurons, all the parameters are activated, but for conditional computation, depends on the input data, certain part of the network is not activated, meaning that they are not going to participate in the forward and backward pass. So what does this mean for your GPU? You know that these characteristics of GPU computation. It is good at matrix multiplication. We call it arithmetic computation. This is what GPU is good at. So some concrete example of conditional computation. One is in binary layer. Basically, it depends on your ID. A certain parameters is not updated. And same, our use case, a mixture of experts. Because the gating only routes input data to top K experts, a lot of experts are not updated. Now, with all the fundamental knowledge we just equip ourselves, we're ready to learn about the bottlenecks of MOE and how Google's 2017 paper solving these 3 bottlenecks. They are shrinking batch size, low compute communication ratio, and the imbalance of experts. Now, let's talk about the most important problem here, the shrinking batch size problem. So this is what we're visualizing that happens in a single worker. It has received the input batch size, which is 1024, and imagine we now have this setup where the gating network will select top K every time and route the input data to top K equals to 4 experts, and in total, we have 1,000 experts. So what happens now is that even though you have 1,000 experts, but only 4 will receive input data. So although your input batch size is 1024, but actual batch size for each expert is actually only 4. The calculation is like this. So you have your total input size as your batch size, but then you only pick top 4. You also have 1,000 experts hosted in this machine. And each expert only receives 4 samples. And remember the characteristics of GPU? It's good at matrix multiplication, but it's not good at branching. So the larger the batch size, the higher efficiency GPU calculation is. And right now, each expert only receives 4. That is a total undermining of GPU capacity. Especially when you are hosting 1,000 experts in this one worker, but each one only has 4 samples received. This is a huge waste of resource. So what is the solution? The 2017 Google paper actually provided a very intuitive solution. Instead of hosting 1,000 experts in one machine and have them underutilize the GPU resource, the solution is that for each machine to only host a partial number of the total number of experts. For example, device 1 hosts like 3 experts, and continuing this, each device hosts different experts. Why does this help? So as we just talked about, the MOE has two steps. One is the routing step. Each device still has its local gating network. So this gating network will tell what for these input data, which expert should it be routed to. But now, if you think about this from the expert network perspective, previously, it only received data from its local machine, but right now it will receive data from all the devices. So the difference is reflected here. And as you can see, now we're able to improve the batch size for expert by a number of D, which is the number of devices. Here is a side-by-side comparison here. As we just discussed, in the traditional approach, each device hosts both gating network and all the experts. But in this paper's approach, it's saying that for each device, it can keep hosting the gating network. But for expert network, it only needs to host a partial number of experts. And these experts will receive data from across all the devices. Hence, it will be able to increase the batch size for each expert by a number of D. So another problem is the low compute communication ratio. As we just have discussed, after the improvement with mixed data and model parallel, there are 4 steps for MOE. So step 1 is compute the gating network. This will decide where the data should be routed to which expert. So then there's a communication step because you need to send the data to the right device that hosts the assigned expert. The expert calculates the result, and the result is sent back to the original device. There are 2 steps of communication, there are 2 steps of computation. How can we increase the compute communication ratio? Let's look at the complexity here. So this first communication step is bounded by the input size. This last one is bounded by the output size. The leverage here, we can see is the hidden size of your expert network. So this is why the paper wants to increase the hidden size. Essentially, as we just discussed, the communication cost is bounded by the input size and output size, but the computation cost can be adjusted based on the hidden size. So our solution here is increase the hidden size. This will not only make your expert stronger because it's more complex and has more parameters, it will increase your compute and communication ratio and better leverage your GPU. So one last common problem about the MOE is load imbalance of experts. The interesting thing part is this is a reinforced problem. For example, the gating network starts to find that one expert is particularly strong, and as the training process goes through, it will assign more and more data to that expert, so causing that expert having more load than others. This is fine, right? Sounds like. But this also means that an underutilization of GPU time. First of all, having one or a few number of experts handling too much data will have OOM issues. And secondly, we talk about this load balance and imbalance. Having one expert handling too much data means that other network might have to wait for this expert. And what do they do when they wait? Nothing. So it's idle, underutilization of GPU time. So now let's look at this paper solution. It's actually quite vanilla. It added a penalty for load imbalance in the loss function. Lastly, let's talk about experiment results. This paper tested their idea on the 1 billion word language modeling benchmark dataset. As you can see, their MOE model has higher flops per GPU. This shows that model now is better at GPU utilization rate due to increased batch size for experts. Also, you can see that they are able to improve the training efficiency with larger models and now lower perplexity rate. So that's it for today. We went through the fundamentals of distributed training, conditional computation. After that, we went through the 3 bottlenecks of MOE scaling and how the 2017 Google paper resolved this. I hope it's helpful. Thank you for watching.